Hi, this is Steve of KStevMath here. We're about to do a new video from our middle school math course, lesson 2, which is all about place value. So last video was about exponents. This video is going to build off of that, and we're going to talk about place value in general, and it's basically all leading us somewhere, okay, because this course in general is going to help us have a really good understanding of place value and decimals and all of that jazz all together. The only thing better than you watching this video with me would be if you also took notes while you were watching it. Now that can be really tricky, especially if you haven't taken notes before in math, but I've got something to help you out. If you will go to the link down in my description, I have a notes page that you can download and print, or download and put into a OneNote or some other inking software, and you can take notes along with me that you can then look back on later whenever you're needing to go over something, or if you get stuck while trying to do homework or things like that. So that link is down in the description. You can go there to my website where I've got a free, let me just say that, free notes page that you can use to go along with this. Now that we've got that out of the way, let's get started with our lesson on place value. So on the one hand, I think it's probably pretty safe to say that you have, at this point in your math career, heard of place value before, although you may or may not realize what the actual name for it is. So place value is a way to describe how large or small a number is, or it's also just the way that we name numbers, so that if we are both talking about a number, we know that we're talking about the same number. And I think part of this is maybe, something that's not super necessary. Like, I can just describe a number to you. I could just tell you the numbers that are involved. But we use words like thousand and million and billion to help us convey the idea of how big a number is. Or at some point this year we'll talk about decimals and their place values, and so we can also use it to talk about how small a number is, which can be super helpful. Just as I was saying that, I kind of had this like epiphany of, well, okay, billions and millions, that's a nice set of words to have, just so that we're not constantly having to write it out. I've had that thought before, but it just came to me again. If you're talking about something and everything you're talking about is in the billions, like money or maybe population of something, it's nice to be able to kind of abbreviate it with the word billion or million or whatever it might be. But we have place value that represent each of the digits in a number, and that helps us to talk about the numbers in the same way. So for humanity currently, as far as I know, all of humanity right now, we use what's called a base 10 system. And so that is because there are 10 numbers in our system. And you might be thinking, no, there's 9. But don't forget about 0. 0 would be our 10th number. What that means, that we have a base 10 society, is that we every 10th number that we count to, we kind of carry to a next place over. There are other ways that we could do this. Computers, for instance, use base 2 in their most machine-like, whatever you want to call it, like in the depths of computers, they're using what's called binary language, and so they're counting just with 0 and 1, which is both fascinating and just, I don't even really understand how it works, but it's really cool. So we use base 10, and I think the best reason for that is because of the number of fingers and toes we have. I would guess that has something to do with why we've all gravitated toward base 10. But enough about base 10. Let's talk more about place value. Just kidding, let's talk about base 10 some more, sort of. So in the last lesson we talked about exponents and how exponents represent repeated multiplication, and so now let's think about it just with tens, because we are a base 10 society, and basically everything we do, kind of, whether we realize it or not, kind of revolves around this whole idea of 10 being a number that we like. So 10 to the first power, if you remember back to what having a first power meant, it just means we have a single 10. So 10 to the first power is just the number 10. 10 squared would be if we have 10 times 10, which gives us 100. And if you have not already encountered this really, really cool trick, whenever you're multiplying by things that have zeros on the end, on the far right, you basically can ignore those zeros and multiply the numbers on the left and then put in the zeros later. I don't know that I'm explaining that super well, but let's give it a try with 10 to the third. So the idea would be 10 times 10 times 10. Now, we can do 10 times 10 and get 100 again, and then when we do 100 times 10, so what I'm saying is we can ignore the zeros and just do 1 times 1, but then because there are 3 zeros, our answer should have 3 zeros to the right of the 1 that we came up with. So 100 times 10 is 1,000. Do you notice anything, any sort of connection or pattern between the exponent we're raising to and how many zeros there are? Hopefully so, because math is all about finding patterns and making sure that those patterns actually work out to be mathematically sound, and in this case they do. If I do 10 to the fourth, which is 10 times 10 times 10 times 10, then that means that I would have 4 zeros, and so that gives me 10,000. And as I'm going through these, I'm realizing I am using those place value words. So 10 to the first is 10, so we're talking about the tens place. That's where our 1 is in this situation, is the tens place. 10 squared is 100, and so now this 1 is in the hundreds place. And so hopefully, I would imagine that you've encountered these words before, but at some point down this list, maybe they'll stop being as familiar depending on things. We often will put a comma every 3 spots to help us keep track, because if you just have a whole bunch of numbers in a row without anything separating it, it can be hard to keep track of where you're at. If you've ever tried to memorize a long number, I think you know what I'm talking about. But also, if we're just talking about thousands, sometimes we won't write it. So the first time I wrote it down, I did not have a comma there. I've only added a comma now that I'm talking about commas. So either one would be fine. But anything after, anything with bigger place value than 1,000, I would say put commas every 3 places from the right, so that you can keep track. Because it also helps you keep track of what place value you're on. So 10 to the third is 1,000. So this 1 right here is in the thousands place. So then 10 to the fourth is 10,000. And these names are probably not going to seem very original. This is the 10,000s place. And we could just keep going. So each of these that we're timesing by another 10, we're going to end up with another 0. So 10 to the fifth would be 100,000. And we call this the 100,000ths place. And then 10 to the sixth would be 1 more 0, which gets us to 1 million and means that we need another comma. So this is the millions place. 10 to the seventh would be the 10 millions place. And this pattern just kind of continues this. So we have thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions. That pattern continues, although we do get to a point where it just is such a big number that we don't encounter it enough to actually need words for it, or maybe there are words for it, but they're just not common knowledge. It's not something we think about. So this is 100 millions. What I mean by that is you probably do know, or once I've said it, we'll say that the next one is familiar. I didn't write down 10 to the ninth, but 10 to the ninth is the billions place. That's probably a word that you've heard before. And then if we go 3 places more, after billions comes trillions. And the thing with that is that a trillion, even if we're talking about money, we've got millionaires, we've got billionaires, maybe there's a trillionaire. I'm actually not sure. I don't think so, because just the sheer volume, whenever you think about how big a trillion is, it's not something that we have, even with money. We're in the billions as far as population goes, right, on Earth. Whenever we're thinking of super, super big numbers like trillion or above, more likely what we would be looking at are things like distances, like in the galaxy or universe, whichever. And so there are other things we do then in math to kind of make it so we don't have to talk about such large numbers. That's a whole other conversation that we could have. But so billions are a thing. Next would be trillions. I don't know if the next thing is quadrillions, but that would be one. That would be my guess because of, you know, billion starts with bi like bicycle, trillion starts with tri like tricycle. So I would guess that the next one would have something to do with 4, and quad is one of the things that we use with 4. Totally getting off on a tangent here, so bringing it back. This is repeated multiplication with tens. Now let me ask you something that you maybe have not seen before. We just did 10 to the first through 10 to the 8th. What would it mean, do you think, to say that we have 10 to the 0? What does that mean to have no tens? What would make sense? Or the other way to think about it is if 10 to the first has 10, which has a single 0, then what would it mean if we had 10 to the 0, meaning we have 0 zeros? You maybe, if I made you guess, you probably guess one of two things. You'd probably either guess that the answer is 0 or 1. And the correct answer is 1. And now that I'm going through this, I'm like, did we talk about this in the last video? I can't actually remember. So anything to the 0 power ends up being 1 because it's this idea of we're talking about having a number, but the simplest number possible is one way to think of it, which is 1. We have something. Okay, we just don't have much of that something. And so that's why it's 1, not 0. There's lots of reasons that we can go through and see why it makes more sense for it to be 1 than for us to say that it is 0, but some of that we need more math before we can really talk about. So 10 to the 0 is 1, anything to the 0 power is 1, and that's a really cool fact in my opinion, and hopefully in yours too, about math that is just kind of weird. But makes sense if you think about the pattern of if we're going backwards. If 10 squared has 2 zeros and 10 to the first has 1 0, then 10 to the 0 should have 0 zeros. And then if you try to go back even farther and talk about negative numbers, then it gets a little it gets different. So that will be something that you do in pre-algebra if you don't encounter it before then. So get excited about that. So to kind of sum up place value, or to look at it kind of in this way, we going from right to left here, you've got the ones place, tens place, hundreds place, comma, thousands place, 10,000s, hundreds, 100,000s, I mean, comma, millions, 10 millions, 100 millions, comma, billions, 10 billions, 100 billions, comma, trillions, and so on. And so it's this really cool pattern that we've got for naming, so that we don't have to keep, like, it's not like we named them all completely different names, which would make this harder to remember. So that's kind of a summary of our place values. And like I mentioned earlier, we will eventually talk about decimal places, which would be to the right of what we've got right now, and how they are named and that sort of thing. So one of the cool things about place value, and in fact one of the cool things about powers of 10 that we can see, is we can think about it kind of as dimensions. And so perhaps you've seen place value blocks before, hopefully you have. I'm going to use those to talk about place value in the context of what we've already talked about, and hopefully to kind of give you a concrete idea of what's going on. So let's look at this and see what's going on. Okay, so when we look at place value blocks, we have ones here, right? So this is one block, and so we can count these blocks if we wanted to, right? We could say, okay, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I've got 10 blocks. But then what I can do is, typically with place value blocks like this, then they have 10 size blocks. So what I mean by that is blocks like this, that there, if you count, there's 10 of these, or we could line them up next to each other, and that would help us see, right, that there are 10 of these. And so this gives us the idea of, we have ones, so we have these blocks that are just one block each. but then we also have these blocks that are 10 each. So this would be our tens is what would be represented here. And so then we could think about, okay, well, there may be 100 of these 1 blocks here, but is that really the best way for us to represent 100, is to have 100 one-size blocks, or is there some other way to represent it? And of course there is, that we can represent 100 blocks together with basically, well, I guess we could have done it, we could do it multiple ways. We could take 10 blocks, right? That would be 100. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or we could just have a block that is 10 by 10. And so these are all, you know, they're not actually blocks. It's just got scratches on it to make it look like they were blocks. But now all of a sudden we've got 100s. And so it's basically this idea that instead of having to, it's almost like instead of having to just count by ones, or even count by tens, or even count by 100s, we can count by these bigger numbers, which is great. And then we might look at our 100 block and we say, okay, well, what if I have a whole bunch of these? What if I have not just 100, but 200, 300? What would our next shape be that we would look at if we had, I don't know, say 10 of these? So 400, 500, we're getting there. Should have taken these out of the bag before I started. 6, 7, 8, 9, 10, 100. Wait, that's not what that's called. 10 100 blocks here, I think that's 10, would actually be the same as a 1000 block. In this block, if these were actually made out of little one-size blocks, which I don't think they are, I think it's just a whole hollow piece of plastic that has ridges on it to make it look like they're blocks. But this is 10 by 10 by 10, okay, 10 on each side. And so this would contain 1,001 blocks. So I think this is neat for a variety of reasons, but from the idea of place value, we have this idea of kind of containers, that we have ones containers, which we might think of just as being our like kind of base container. But whenever we get enough of our ones, it kind of reminds me of Monopoly also. We get enough of our ones, we get to trade them in for a 10 block. And then we get enough 10s and we get to trade those in for a 100 block. And we get enough 100 blocks, we get to trade those in for a 1000 block. And that's as big a block as I have. And also after 1000, it gets a little tricky on the dimension side of things, because the other thing we've done here, which you may or may not have heard before, is we've basically been talking about dimensions. That if I have a point has no dimension. This has no, we would consider this to have no length or width. Yes, literally I could measure it with a ruler, but we would consider this to represent no length or width in math. Whereas a line we would consider to represent going this direction, but we wouldn't say it's wide this other direction. So we'd have a length here. This is a one-dimensional object, a line, because it's going in one direction, left and right, not in both directions. Where this, a square, would be considered two-dimensional. And if you've done two-dimensional shapes before, probably at some point, and I'm sure you'll talk about them again, a square is a two-dimensional shape. Just like a rectangle, a circle, all of those are two-dimensional. They're shapes that we can draw on a piece of paper, which a piece of paper is kind of a two-dimensional object. Whereas whenever we come to the cube, a cube is a three-dimensional shape. And so it might actually spark your curiosity here of, well, what would it mean if there were 4 dimensions? How could we represent that? And that's where it gets really tricky and really abstract in math, and you know what? You may just not be ready for it yet. I don't know that I'm ready for it yet, actually, but it's a fascinating idea, and it's a really neat idea of these things can represent the dimensions we have. And so 10 cubed here would be like having 3 dimensions, just like volume is 3 dimensions, right? We can find the volume of this. If you're familiar with volume, we can figure out how much space it takes up. Whereas with this, it'd be more like we're thinking of a square and thinking of area, which is something that we measure in things like square inches or square centimeters. And so there's all these things that can be related here with the exponents we talked about last time, and now with our place value and 10 blocks, and so it's really cool. This was all to say that if you are shown pictures that look like either just a single square or a 10 block line, right? 10 of them in a row, sorry, or our hundreds block or our thousands block, we can represent these with powers of 10. There are 0 tens here in a 1 block. There is 1 set of 10s here in a 10s block. Whenever we get to the square, it's kind of a little bit trickier what we're talking about. We're talking about being 10 by 10 whenever we're talking about a square. So that would be 10 squared. And then for our 1000 block, we're talking about something that would be like having 10 by 10 by 10, so 10 cubed. So not sure how much sense that makes, but I wanted to give it a try with these manipulatives to explore this idea of how 10 blocks can be represented in real life. So I've just shown off in example 1 my base 10 blocks, which there is a link in the description if you'd like to pick up a set of those. It is an affiliate link on Amazon, which means if you purchase them using that link, then I get something from it. I don't know what, because it's never happened before, but if you know, it doesn't cost you any extra. So if you wanted to help me out and click on that link and buy them, just that'd be great, but you don't have to. Anyway, so this example 2 here, we are filling in, there aren't any blanks. I meant to put blanks here and there aren't any, but we're basically answering the question 10 to what power equals, and then depending on the power, we're gonna answer it. So the way we do this is repeated multiplication, but because it's tens, there's this really cool trick which makes us not have to think about it. 10 to the third is 1 with 3 zeros. How do I know it has 3 zeros? Because that's a pattern that we looked at earlier, right? So 10 to the third power, it would be 1, 0, 0, 0, 1000. 10 to the fifth power would be a 1 followed by 5 zeros. Now, you may want to write it down from right to left, or write it down and then add the commas, because okay, there's 5 zeros, because otherwise you might not know where the comma is supposed to be. I personally have trouble visualizing numbers in that way, with like how their size and where the comma should go. So I had to kind of write it down first and then figure out where the comma needed to be, which was right smack dab in the middle there. So that 10 to the fifth power is 100,000. And then 10 to the 0 power, there are no zeros because it's to the 0 power, so it is 1 as my answer. So not too bad, a lot better than trying to do like 7 to the fifth power, because then you have to do 7 times 7 times 7 times 7 times 7. I've lost count of how many 7s, but still super useful to be able to do this because of how much we do things with tens and place value. Okay, this time I remembered to put the blanks. Example 3, fill in the blanks. So now we're starting off with a number and being asked to write it as 10 to some power. So 1000 equals 10 to what power? Now, I mean, we could, you know, write out how many tens we think it takes and multiply them together and kind of guess and check. But we can also just use that trick that we talked about, which is the number of zeros is equal to what the exponent should be. So there are 3 zeros for 1000, so this should be 10 to the third power. For 1 million, we have 6 zeros, so this should be 10 to the sixth power. And for 1, there are 0 zeros, so that would be 10 to the 0 power. Very cool, pretty easy, hopefully. So, yeah. So example 4 here has us change gears a little bit. We're still going to be in the world of place value. It says write the numbers first in expanded notation and then in exponential notation. And I think the idea here is that you've probably seen expanded notation before, although it could have been a while. And then what would be new would be a twist on that, which is called exponential notation. The idea with both of these is that we want to make it really clear that when we're talking about a number like 573, that we are talking about 5 100s, 7 10s, and 3 1s. And so we write that out in expanded notation by doing 5 times 100 to show that there are 5 100s, plus 7 times 10, plus 3 times 1. And as far as usefulness in general in math, like, or I guess usefulness in the real world, like when would you ever want to write out a number like this and have it be helpful to you in the real world? I'm going to be honest, can't think of anything off the top of my head. This is one of those times where being able to write it like this and understand what the number actually means conceptually will give you a better understanding of math, which will just help with other concepts later down the road. I can think of ways in which being able to think of it like this will help you in algebra. That doesn't mean that if this is totally not making any sense to you that you'll do poorly in algebra. It's just that I can see a relationship. I can understand why we point this out, that there are 5 100s, 7 10s, and 3 1s. So just so you know, that it's not just this random thing that doesn't have any usefulness. So that's expanded notation. Let's look at exponential notation. The difference would be that instead of writing 100, we'd write 100 as 10 to a power. So 5 times 10 to the second power, and then we'd write 7 times 10 to the first power, and 3 times 10 to the 0 power. So we'd want each of them to be a power of 10, and that power of 10 represents the place value that we've talked about. And so for this particular number, that did not really make it any shorter for us to write it, because we had to write 10 to the first instead of 10 and 10 to the 0 instead of 1. But if you can imagine bigger numbers, you might be able to write less than, like, say that we had a number that was like 1 billion. Well, writing 5 times 1 billion takes longer than writing 5 times 10 to the 9th power, whatever it would be. So keep that in mind, that just because it wasn't shorter this time, I think the intention is for it to be shorter, to write it in exponential notation. So let's do 2001. So in expanded notation, regular expanded notation, we would say, well, we have 2 1000s, so 2 times 1000. And then we can skip over the hundreds and the tens because both of those are zeros. And so then we can go straight to 1 times 1. And then that's it. So our exponential would be 2 times 10 to the 3rd power, because 1000 has 3 zeros, plus 1 times 10 to the 0. And now the next thing we're going to do is actually go backwards, look at it the other way around, taking something in expanded notation or exponential notation and writing it as a normal number. Example 5, express as a number in standard notation. So this is the kind of number we're used to dealing with. Not in exponential notation, not in expanded notation, just a regular number. And we could also do this from exponential notation by thinking about how many zeros there are with whatever exponent it has. So this says 5 times 100 plus 2 times 10 plus 7 times 1. So 5 is in our hundreds spot, 2 is in our 10 spot, and 7 is in our 1 spot. So our number here is 527. So if you haven't already thought to do this, try this next one without me. Pause the video and then see how it goes. Okay, you're back. Good. So 3 is in the 1000 spot. There isn't a hundreds spot. We don't get to just skip it this time like we did in the last example. We need to make sure to put a 0 in the hundred spot as a placeholder. 6 is in the 10 spot, and 1 is in the 1 spot. Now I'm wishing that I had done another one in expanded notation. So let me do that real quick. Not expanded. These are in expanded. Exponential notation. Voila! We've got a new example here that we can look at. So I made this one a big one in the hopes that we will in fact see how, or imagine how it is faster, easier, faster, whatever, to write it as exponential form instead of having to write out all those zeros. So 8 times 10 to the 9th power means that I have 8 followed by 9 zeros, but not all of them are zeros, right? I have 2 times 10 to the 6th power, and I have 5 times 10 to the 3rd power. This seems to me like the case where going from the right would actually be easier. So I have this 10 to the third power is 1,000, right? So I have 5,000. So 3 zeros and then a 5. The next number I have is a 2. And this was 6 of them. That would be millions. As soon as I actually finished writing this, I regretted picking such large numbers, because this is not the kind of math my brain really naturally works well to. I don't know if you're feeling that, or if you're like, oh, this is so easy. Why is it taking you forever? To each their own, okay? So this is 2 million, which by pattern makes me think that this is probably 8 billion. So we need a couple more zeros, and then our 8. So this is 8 billion, 2 million, 5,000, which is a very large number. Hey, thanks for watching. This was really fun to kind of explore the idea of place value with you, and I hope that you will continue watching these videos and learning middle school math from me. If you haven't already, please head over to my website, KStevMath.com, and check out the resources and things that I've got going on there. You can do this whole course with me this year if you'd like to. Just head over to the website in the description, or you can start off by just going to KStevMath.com and navigate there yourself. What else? What else am I supposed to say at here at the end? Subscribe? Yes, do that. Like? Absolutely, please do. Probably can't comment because I think this is going to be labeled as for kids, just because of where I think the majority of people watching this video for learning purposes would be. What else? I'm forgetting something. Oh, if you liked the blocks I used in this video, there's a link in the description below. It is an affiliate link, so if you go there, I do get something out of it, but so do you, because it's a high quality product that I've used now on video once, and that my toddler has enjoyed and is old enough not to eat the ones blocks, which is really helpful there. So again, thank you for watching, and hopefully I'll see you in the next video.